So what we're going to do in this video is we are going to make the analogy between the mechanical oscillator with a mass on a spring from 801 and the electromagnetic oscillator with an inductor and a capacitor from 802. We're going to make that mathematical analogy precise. So in the 801 oscillator, we have a mass with kinetic energy. And we saw that kinetic energy was analogous to magnetic field energy. And so that suggests that when we make this analogy precise, there will be a relation between M and L. And as this mass moves, it has a velocity, it has a position. We saw in the analogy that kinetic energy was analogous to magnetic energy, and that suggests that the velocity of the mass is analogous to the current. We'll see that we need to adjust this very slightly in just a second. Potential energy was analogous to electric energy stored in the capacitor. Potential energy analogous to potential energy of the spring analogous to electric energy of the capacitor. That suggests that there's a relationship between the spring constant K and the capacitance C. This is actually not exactly right yet. We'll make it correct in a second. And well, how much potential energy is there? That was determined by the value of X, which tells you how much the spring is compressed by. How much electric energy was there? That was determined by the charge Q on the capacitor. That tells you how much electric energy is stored in the capacitor. That suggests that there's an analogy between X and Q. And again, this is not yet quite right, but we're going to make it correct in just a second. So in this oscillator, the mass moves back and forth. That means X is oscillating periodically. The velocity of the mass is oscillating periodically. Those two are out of phase. When X is at its maximum, the velocity is 0. When X is 0, the velocity is maximal. In this oscillator, Q and I are oscillating, and they are out of phase. When Q is at its maximum value, there's no current. When the current is at its maximum value, there's no Q. OK, so I said these weren't quite right yet. How am I going to get them right? Well, I'm going to use equations. And I'm going to compare the equation F equals ma with a being dv dt. So this is m dv dt to the equation for the electromotive force across the inductor, which is minus L di by dt. And I now realize that if I want to make the analogy by having m correspond to L, then I need v corresponding to minus I. So I need a minus sign here. And let's now look at the energy, the kinetic energy. So the kinetic energy is 1/2 mv squared. And the magnetic field energy, UB, is 1/2 Li squared. And we see that this works. So 1/2 mv squared corresponds to 1/2 Li squared with these identifications here. So my kinetic energy up here corresponds mathematically to my magnetic field energy down here. OK, but now I want to check my K and X connecting to C and Q. And there are two ways of doing this. Let's do the easier way first. Let's check the force, the expression for force, not in terms of ma, but in terms of the force from the spring. So the force due to the spring is minus kx. And then let's check the voltage, not across the inductor, but across the capacitor. And that is Q over C. And so now to draw the analogy, I need to relate K to C and X to Q. And you see there are different choices that are possible here. But the way that I've chosen my signs corresponds to relating x to minus q. So x is analogous to minus q. And k is analogous not to c, but to 1 over c. So it's, to make this mathematically correct, I have to relate k to 1 over c. What about the electric field energy? Well, that corresponds to the potential energy in the mechanical oscillator. That potential energy is 1/2 kx squared. And the electric field energy in the electromagnetic oscillator, in the LC oscillator, that electric energy is 1/2 q squared over c. And you see that this works. I have 1/2 q squared, x squared. X squared becomes q squared. The minus sign doesn't matter in that case. And k, 1 over c, k, 1 over c. So this, by the way, this, maybe I should call this the kinetic energy in the oscillator. The potential energy in the oscillator, U, becomes analogous to the energy stored in the electric fields in the electromagnetic or 802 oscillator. So there you have it, the full analogy. And now every equation that you learned how to solve in 801 relating to a mass on a spring, you can translate into a true equation describing this electromagnetic oscillator, this LC oscillator, if you replace V's by minus I's, X's by minus Q's, masses by inductors, spring constants K by 1 over capacitor. That will turn this math into this math precisely. Okay, so let's actually use this analogy. Several videos ago, when we refreshed our memory of this mechanical oscillator, we found that the period of its oscillation was 2 pi over omega, where omega was the square root of k over m. And so the period then was 2 pi times the square root of m over k. And we can use this to figure out, using this precise translation of the math of one problem into the math of the other problem, we can use this, what we did for the 801 oscillator, for the mechanical oscillator, we can use it to figure out what the period of this oscillation is. Remember, we had a 4-chapter story here. Q started out positive, then it became 0, then it became negative, then it became 0, and then it became positive again. The electric energy went to magnetic, to electric, to magnetic, to electric. And in that 4-chapter story, what's the period? Well, the period is going to be 2 pi over omega. But omega, the analogy says that instead of square root of k over m, if I replace k by 1 over c and L by m, that tells me that omega is square root of LC. And that tells me that the period of the electromagnetic LC oscillator is 2 pi times the square root of LC. And you'll remember several videos ago now, we did a little bit of dimensional analysis after we had studied RC circuits, which had a tau, a decay constant, a time constant. And then we had done RL circuits, and they also had a tau, a time constant. And then we wondered, is there any way of combining L and C to get a time, and might that have something to do with LC circuits, which we hadn't even done yet? We did the dimensional analysis, and we realized that square root of LC was a time. And what you now see is that 2 pi times the square root of LC is the period of the oscillation of the LC oscillator. So an LC circuit doesn't have a decay constant. It's an oscillator. It oscillates back and forth, back and forth, back and forth, back and forth forever, just like a mass on a spring. But it does have a characteristic time. That characteristic time, instead of being a decay constant, that characteristic time is a period, and the period is indeed 2 pi over square root of LC, as we intuited using dimensional analysis several videos ago.